So in chapter 7, we have these additional subjects, one of which is about the ability to add hinges to your frame elements when running those computational analyses. I don't know if you probably came to this point by creating your own element matrices and structure matrices, etc. But if you don't do anything additional, obviously the conventional regular element matrices, when they come together, they all simulate a perfectly joined, fixed joints between each element. So we have to do additional work to simulate hinges. And again, I think I covered a little bit about how the element matrices change as we add hinges with these zero rows and columns being introduced as we add more hinges. And we talked about how these matrices on their own would never be able to, they wouldn't be invertible, they would be singular, and how adding multiple of these elements might end up creating a matrix that is actually invertible. And here it's basically going over different scenarios where multiple hinges are added to the beam in the beginning of it, at the end of it, and both of those being hinged, and then goes over how the hinges are actually changing the behavior of the structure. I wanted to take this opportunity to sort of cover how important it is to have hinges, or be the ability to how important it is to have the ability to put the hinges in certain locations, and why we can't have a hinge at the joint like we sometimes conventionally do when we go over trusses. So I have created a few files to cover that. So I have a structure here where I have, let's say, no hinges, and I added a little bit of moment in the center. It's a pinned structure from all corners, and of course, the deflected shape, you would expect it to be as such, right? Because we are holding this joint and rotating it. And let's take a look at the deflected shape and see why we can't have this point as a hinge. If we say this joint is a hinge, can anyone tell me what might be an unexpected limitation that come with this? Let me rephrase that. Why do we put the hinges at the ends of each element instead of at the joint? Can anyone speculate on why that would be a limitation? Okay, let me share my ideas. Let's say we have a structure as such, but we want to, let me remove that load. Let's say I have some distributed load on it, and I have this specific behavior. If I make this a hinge, right? Theoretically, if we assume a pin exists here that all of these elements are connecting to, I will have a behavior where I will never be able to connect or control if the moment from this element shall flow to the column, right? While if I have the hinges at the ends, I can control where the moment shall flow. So independently, I can decide which one of these elements will be fixed connected to the column and which one of these will be simply connected, right? And you can't really do that if you make the joint itself hinge. or a pin. So let me remove these distributed loads and put my rotation there. Let's take a look at how this behaves when I turn this joint, right? If I have a hinge here, what do I have? The joint rotates, but this specific element is not affected by it because I allowed it to rotate here. If I do the same thing here, now these two don't rotate, but the joint still rotates. The kind of confusing thing here is that this, after the hinge, in most software, you don't see a rotation because this is assumed to be right up against this point, right? It's almost zero length joint, basically, right? A zero length distance from the end for this hinge. So I can do the same thing here. Now I am rotating the joint, right, with an applied moment there, and only one of these elements are affected. Now, what happens if I turn also this into a hinge? Now I got, sorry, let me just do the second one. Yeah, now I got a singular structure, so I can't get a result. Why? Because this joint is now free to rotate as it pleases, right? So to simulate this, I created something here that basically includes these short links where the joint is a separate structure. So instead of having that a zero offset for the hinges, right? I made them, let me make these the same again so you can compare those. So what I did is I added these short links to offset the hinges a little farther so you can see how adding 3 hinges actually works. It makes sense, right? These won't get a lot of load or no load because of the because they are pinned and they have a hinge, so you're not going to get any moments on them. But there's at least one element that can take that moment, right? By looking at this. Now, what I want you to see is that if I add a pin here, well, this is again not stable. It just has excessive deformations. So instead of flashing, it's just showing excessive deformations, which is another way of um, showing us that it's singular. In floating point operations in computers, sometimes the determinant does not come out exactly zero, so it's still kind of invertible, but not really in the engineering sense. So what can we do to see that deformation? I'm going to remove the load, and instead I'm going to put a rotation there, like 0.01 radian. And if we look at that, you can see that this joint now, because we also broke this end, right, turned that into a hinge, it's free to rotate, which tells us that, okay, by putting the hinges on the connecting elements, we have the flexibility to decide exactly how the load will flow. But we also have to make sure that we don't have everything connecting to the element as a hinge, because then we have a mechanism at that joint specifically. In this case, you can't see it because joint has no dimensions. But when I add the dimensions, you can see that only when you have at least one element connecting to the joint without a hinge, you can have a structure without a mechanism, basically. So we have to keep that in mind. And this is what I wanted to cover in regards to hinges and their locations. Do you guys have any questions?
Yeah, I mean, I always wonder this because during whenever we use SAP or something,
Mm-hmm.
we would always at a, let's say an intersection at a joint, you would release the moment in every single element except for one.
Mm-hmm. This
And
is
if
why, basically.
so
Yeah.
this is the reason why kind of like
Yes.
creates its own mechanism. Okay.
Exactly. So the joint itself becomes sometimes SAP does some weird stuff. So you have to be very cautious with SAP because they have what they call soft springs. So let me show you what that would mean. Let me see if I have something soft. No, but I can add something. Let's call it soft spring. Let's make it polystyrene or something. Update that section. So, as you said, right? I'll remove this deformation and replace it with a moment again. Now it's crazy, right? But what I can do is I can add a soft spring. That would be this guy. Now, I guess it's a little too soft. Let me add just a little bit more. See, now I can see some deformations, even though it's actually a mechanism if this is not here. And SAP, sometimes to be able to solve structures that are not perfectly stable, just to be able to show you what's going on, it automatically adds these soft springs to the structure. So you have to be very, very cautious. Always look at the deflected shapes because those soft springs are, as the name implies, they are soft enough that you can still see the load being, flow. Basically, the load flows, but you also will have large deformations. So be careful about that. But yes, you're right. This is the reason why we have we have uh, you know one of those hinges not added because otherwise your joint becomes a mechanism. So let me. If you guys have no questions, I'll proceed to the next item. Okay, I hear yes. Okay, so why did I even close it? It was not necessary. So we talked about hinges. I'm going to, this is all showing how to member releases, how to actually do that in the computational side of things, which is good. It is necessary to know. Okay. Support displacement effects. I think we talked about this the last one, so I'm going to leave this to the end. Or maybe let's do it. So on the support displacement side, I've created a nice little demonstration for you to give you a little bit of a feeling on support displacements. So I have this truss, and I am putting a little bit of a deformation on this support. So the support moves in this direction. Usually you wouldn't expect it to be moving against the load direction, obviously. Think about it as, a support where we can actually pull it back. And I pull it 1.03 millimeters. And this is deliberate for some other reason. But when I pull this 1.03 millimeters, let's see if the engineer in you can predict how much of a movement I'm going to get at this point. Can anyone guess how much of a movement I'm going to get at this point? I'll give you one clue. This and this element have the same length, so it's typical. They're squares. Can anyone guess in which direction and how much of a movement are we expecting? Direction is a little easier. Anyone? Bad guesses are also welcome. Mediocre guesses? You can also do good guesses too. It's all welcome. Anyone? Brandon? Are you there? Edward?
I'm here, but
I hear you. Do you
I
have
don't
a
have a
guess?
good.
Think about it like this. Remember, we talked about deformation being linear, right? So rotations become slopes. So I move in this. So you can see that it's going to pivot around this, correct?
So
Because
it's
I'm going
gonna
to
move
pull this.
up.
Right. Okay, perfect. Very good, right? This
Okay.
is going to move up. So we know that whatever this thing is going to rotate, it's going to rotate as a whole body. So if in this distance it moves 1 millimeter to the left, how much is this going to move up? Keeping in mind that rotation is slow, which means all you have to do, is, since the rotation is the same, all you have to do is, it's almost like a moment, right? The farther you are, the more it's going to rotate.
Right.
So if this is a millimeter, this would go up 1, 2, 3, 4,
Times
5
length.
millimeters, right? Because
Yeah.
it's 5 times more. Like, let's take a look at this. You can see that as I move this up, left, this is going to go up, and it's 5 times more. So you can actually see this. If I, you can see that. Let's take a look at the values a little bit. This one's 1.03. This one moves about 5.15. It's actually, it's exactly 5 times, because we have small deformations assumption, right? So why am I showing you this? I want you to see how structures will behave, even if it is almost determinate like this structure, when their supports are actually deforming. The fun case here is this. In the second scenario, where I said, okay, what if I just load it with a certain amount of load? I think it was 50 kilonewtons down at this tip. And it moves down 5.15 millimeters. So what made me, happy was that, so I realized by superimposing these conditions, I made the deformation of this point, at least in the vertical direction, completely zero by, even though it has the load on it, right? So I found a way to cancel out the deformation due to this by pulling this joint back 1.3 millimeters. So in a real world scenario, if you have a long cantilever and you know it's going to deform too much down, you can actually pull the top end or fabricate the top end short this much, so that your deformation, after deformation, right, you basically build it like this, and then after deformation, it becomes basically zero. And actually, there was a case in Brooklyn. I don't know if you guys are familiar with New Jersey Nets. Used to be New Jersey Nets. Now it's Brooklyn Nets, the basketball team. They have an arena in Brooklyn, and that's exactly what Thornton Tomasetti did when they designed a long cantilever. They basically designed it so, let me show you. So this cantilever here, they designed it so it was actually pointing up initially, and after all of the load was put on it, that long cantilever, you can see the cantilever here, this long cantilever came back to its original design dimensions, because it was such a long cantilever that if they started with the original design dimensions and fabricated all of the steel according to the original design dimensions, then it would be sagging quite a bit down, and maybe these facade panels wouldn't fit. There would be a lot of problems. So what they did is they predicted how much it's going to deform first, kind of like cambering and beams, right? And they put an upward pull on it like this, right? And after the load was placed, it came down to where they wanted it to come down to. So this is what I wanted to talk about. Any questions here? Guys? No questions? It's okay. Let me continue down. There's temperature effects. I'm not going to get into that. It is actually a fun subject, but I don't think I'm going to be able to demonstrate anything interesting with it. What else? Yeah, I think in this chapter we are good unless you guys have any questions. Then I'm going to show you, is this substructuring? Let me see. Yes, this is substructuring. I'm not going to get into substructuring yet. Let me show you the rigid links story. So you'll see that there is a chapter here where they talk about rigid links here. So what are these rigid connections? What does it have anything to do with structural design? I'm just going to demonstrate and explain that a little bit. So let me pull up my rigid links demonstration to save a little bit of time. Now, let me start from maybe this end. Okay. So I have a structure like this, okay? And these, it looks like a shear wall, right? Rather than just a column. And we start seeing something that we do not take into account when we're looking at these elements as just a single line element, a frame element, right? Look at this. This is clearly, it's a uniformly loaded structure. One thing that will immediately that you will immediately notice is the uniform load goes all the way to the center of this shear wall. But in a real world application, obviously, we don't have people, let's say if this is live load, right? We don't have people walking into the shear wall. So this is overestimating how much load we're going to be putting on the structure, right? But if we just assume this as a single frame, we have no other option if we're saying that, okay, this is the member and it has this much distributed load. It will simulate the entire length of this theoretical element to be loaded with live load. So obviously that is not the reality. And when the elements are tiny, like these blue frame elements are, the effects are negligible. We don't care. But when the elements get thicker and thicker, the effects become more and more significant. Take a look at the deflected shape here also. You can see that this element is actually deforming down even before it comes out of that virtual area inside the shear wall, which is also not the real behavior. So there's something wrong here, or something not so accurate, but it seems like we can't really handle it with our frame elements, because these are frame elements. I mean, if I make this, that thinner section, then this is, just a column. And if I make it a shear wall like this, then, we model it as such, because don't forget, we have to create some matrices for each of these elements and sort of solve everything kind of blind, right? Without really fully understanding which term is doing what. So we just need to stick to our rules and invert our matrices, multiply our vectors, and get our deflections and such. So how can we solve the problem of this deformation inaccuracy and also the loading condition inaccuracy? And that comes with what we call rigid links. So if you look at this, obviously this is an element, right? Let me turn one of these into a steel section there. And you can see this is one element, and this is the same thing. Even though this is much wider and larger, it's still one element. This is also one element. What I do is, in this case, because this shear wall is so wide, I make use of these two elements, what I call rigid links. What I did is basically I added and gave a very large area and a very large second moment of area to this element specifically. And you can also use very stiff materials as well to simulate the same behavior. And now this is actually another frame here, right? I have instead of one frame connecting from one node to the final node, there's an intermediate node where I connect to that intermediate node, and then from the intermediate node to the center of this frame, right, there is another element which I call a rigid link. And you can see them here as well. So those rigid links are very, very rigid, and we use them to simulate closer to real behavior. Look at this now. Now you can see that the distributed load is actually not all the way into the shear wall, but to the face of the wall. And that makes sense in most cases, right? Even if it is dead load, if you have some sort of floor covering or something like that, it's not going to go into the wall. It's going to end right here. So we simulate the behavior correctly. And if you look at the deformed shape, now you can see that the deformed shape is also very different, right? I don't see the deformation starting inside the wall, but at the face of the wall, like it would really do in real life. So we make use of these rigid links to simulate a closer to real behavior. And I don't need to really do anything additional other than just define a new frame element that is very, very rigid axially and in bending modes. And if you have more dimensions than 2 dimensions, like I have here, you can add more dimensions to it, maybe torsional rigidity, etc. Add all those and make them really rigid so that you have a way of connecting your frame element to a much thicker frame element or deeper frame element at the point where they intersect each other. This is a very commonly utilized feature, by the way. SAP doesn't do that automatically. At least it didn't do it when I used to use it as a student. But a lot of other software that I used after, throughout my career, actually utilize these rigid links to simulate the behavior. I have another case here where I wanted to show you how adding hinges also make a lot more sense when you use rigid links, right? I use these rigid links to connect these frame elements at the correct location. So when I added hinges, their deformations here, it simply does not make sense. So we have to understand the limitation, because if I know in SAP, at least by default, I think it does not show you the thickness of the elements, and which makes sense, from I guess performance perspective. The computer will have to use a lot more resources to render, 3-dimensional or 2-dimensional thicker shapes than just a line. But at the same time, we have to be cautious. We have to look carefully into how the structure actually looks, and those connections actually how they resolve into a more true to life structural design. So what I did here is add those rigid links to simulate a shorter deformation here. Again, uniform distributed loads again makes sense, and you can compare loads on them as well. Like I'll show you. Let's say this one has 1.56 kilonewton meter. And if we have not looked at our deflected shape, and if we have not looked at our 3-dimensional or 2-dimensional, more realistic views, we may be oblivious to the fact that this number is really not that realistic. I mean, look at the number here. You can see that it is 1 kilonewton. That's 50% of a difference. Very big difference. And in deformation side, I'm sure it's much more. See 2.45 millimeter, and it's only 1 millimeter. That's a 100% of a difference, right? So we have to be cautious when we're designing our structures. And one way of simulating these closer or more realistic behaviors is to use these rigid links. I think I have another structure here. See, yeah. So take a look at this one, right? This one is, let me start by making this all thinner section so you can see a little bit better. Now, if I look at this structure, right, and if I look at the deformed shape, I can, it kind of makes sense. And the thickness of these elements, they just really don't make a big difference, right? Neither on the distributed loads. In this case, there are none. This is loaded at the floor levels with a point load on these nodes. But um, you can tell that the thickness of these elements don't make a big difference, right? In this case. But if we have something a little thicker, maybe not as thick as the shear wall up there, now it is actually, a little different. I mean, even the looks of this is kind of funky, right? Clearly, this element, let's say my floor heights are defined as 3 meters, and this was my floor, right? Or this is my floor level is the third a 3 meter coordinate here from this datum, and then 6 meter over here. So this column looks okay, but these beams look like half of them are in the second floor or the third floor, and half of them on the second floor, and same thing over here. So they don't really simulate a true to life behavior, because it's more common to have the beams sort of defined at the top of their surface, right, at the floor level. So what can we do to simulate this shift? Because I can have deeper, or, let me make this one a little deeper, right? So if I have this is clearly not what I'm going to get, right? They're going to be flush at the top. So I need a way of simulating this being lower than this and load flowing accordingly. And how am I going to do that? Again, I'm going to use rigid links like I did above. See, this is where I sort of cleaned it up. And you can see the corners make a lot more sense. The frame elements a lot more sense. See, I have my beams at their correct length. It leads to some shorter column elements. It doesn't really have to. I did it this way, but I'll show you how else you can do that as well, by not using horizontal rigid links, but making them a little bit more different. See, I have simulated these shorter now, and you can see, let me zoom in a bit. Take a look at this. So this column, it goes from here at this floor level to all the way up to the top of the floor, right? And these can come down or up. One way to simplify this would be, I'll delete all these and make this column go all the way up. But I can still use my rigid links. Keep in mind, my rigid links are really rigid, right? Now, I actually connected it. I will keep in mind, when I look at this moment diagram, right, I will completely ignore the moment diagram of the rigid links. I'm going to just look at the moment diagram of my elements, right, and completely ignore these. And computationally, you may actually, or in a computer program, you may actually just hide those and get a cleaner picture. The software I'm using right now does not support that, but you can see now the behavior is the same. I mean, there's a little bit of a at large deformations, there's a little bit of an artifact happening here, but you can trust me that the deformations, the moment, the shear, they all make sense. So in a way, I made my column the height I want, and I made my beams the depth I want and the length I want by using these rigid links, so that the connection is completely rigid at that point. Now, let me try another thing, right? We talked about the shear wall. Let me apply this. Now, what I can do is I can actually move this, right, down a bit and get it to the flush level and still use my rigid links. If these are rigid enough, it is going to simulate a monolithic connection. This kind of reminds me of reinforced concrete more so, right? Probably for you as well. But you can get similar connections in steel as well, but it's a lot more common to get them in reinforced concrete. And by using these rigid links, we can actually simulate a more realistic behavior of these elements. All right, let me, do you have any questions? Anything to contribute, guys?
I have a quick question.
Cool.
Um, are these elements also used to help model moments due to like eccentricities since it's not perfectly
Yes,
flat?
it will just come from that, right? So if I, yeah, let's you know what, let's why not put that theory to the test, right? Let's say I have a a structure like this, right? And say I have, yeah, let's do with concrete and then shear wall over here, right? If I apply a load of, let's say, minus 180, like this, right? I get a moment diagram like this. But is this really what I want to simulate? Maybe not, because how are you going to get a concrete structure or connection like this, or a steel connection for that matter, right? You're not going to be able to connect two things like this in almost all cases. This element probably is going to be taller, and this element's going to be backed. So what would be the real behavior of this is the question. So let's simulate that. Um, let's say, again, we need to know what the real size of the element is, but let's assume this goes all the way up here, right? And then this is going to be, we're going to have to add an element here, connect them with the shear wall like this, and then finally connect them with the rigid link like this, right? Now, let's take a look at the deformations. Turn this. So you can see there's a little bit of a difference in the deformations, and the top deformation is very different, 0.93 millimeter at this corner, while here we are reading 68, right? It's just not the real behavior. This is a lot closer to the real behavior if we had a connection, if we had a structure like this. So in a way, I simulated an L-shaped structure rather than something that's more theoretical if the connecting elements are thicker. So let's take a look at the moments. Very different. Very different, right? See, this, let's ignore that. But were you expecting a negative moment? Maybe in this box here, right? This box here, it is a good idea. Maybe just let me just show it like this, or maybe even like this. So in this box, maybe it is a good idea to completely ignore what you're reading. But at the same time, this allows me to read what's going on here, right? All I have to do is figure out how long this is. This is 5 meters, so 3 meters on. I have a point here, so I'll just divide it at 3 meters. Now, if I look at the moment diagram, I can read the moment at that point because I designed and simulated my structure a little bit more realistically using those rigid links. Like you said, the story would be very different if, say, we had a thinner section, a thinner section here, right? Let's go with the other section. And so obviously we have a very different behavior now. Let me just slowly move it up to flush. Yeah. See, take a look at the moment here. I'm going to have to move this up. So from the same load, we have different moment conditions at this specific section, right? And different rotations, and it's just a much more convenient and more realistic way of modeling our structures. And a lot of software, commercial software out there, they actually do this automatically. So that's a good that's a good advantage that come with modern software. Okay, what else? So we talked about this, we talked about this. Okay, angled rollers. So another limitation that you might not have thought about is the capability to model rollers at an angle. See, I have a roller here, right? And this one was aligned in a way that the loading condition does not really move it. Maybe I'll add a little bit more uniform load here to simulate. Yeah. Okay, some moment or deflection there. See, I have a roller here which moves in this direction, and you can see U, or the axial deformation at this end of this frame, is 0 millimeters. Makes sense because we made it, a roller rolling in the vertical direction. And then over here I have in the horizontal direction. So I have some lateral load coming. This obviously is turning into a reaction on this end, right? The load coming here with a shear of 1.75 kilonewton turning into a reaction here. And in this direction, the load comes and it leads to a movement in the horizontal direction, and this is resolved by the shear in this. See, 1 kilonewton here, 1 kilonewton comes down and resolved here at this joint. But if somebody said, okay, let's assume this is a 45-degree element, kind of like, let me see if I can write on this. So let's say somebody said, can we have something like this? This is actually a little difficult to simulate. So this is, let's say, 45 degrees. This is actually pretty difficult to simulate with the rules that you learned, because what do we normally do, guys? We find the degree of freedom that's going to be restricted by the support, and then in this case in the vertical direction, right, in this direction, and then we put a 1 there and then put a 0 at the displacement side, and that equation becomes just that. We say, okay, no deformations at this point. So when we solve the structure, we actually get 0 deformations in the vertical direction here, or 0 deformations in the horizontal direction here. But we don't have a coordinate for 45-degree angles. So what do? You can try to write other equations to enforce that behavior, which you technically can, but it's arduous. It's not easy. So just like the rigid link solution, there is a solution possible where you don't really need to worry about changing your equations or how you construct equations, but instead use the already available elements you have to simulate a 45-degree angle. I actually did that here. So this is another theoretical element. I like to use pink for those. And if you look at this, I call this section slider section, and I gave it a very large area and a very small second moment of area. Sometimes they call it moment of inertia. Not really in this case, but the second moment of area is very small comparatively, right? If you look at the second moment of area of this is 10 to the power 6. This is just 10. Why do I do that? I do that because I want this to be able to deform, right, in its lateral local coordinate. Again, its own local coordinate, right? It is free to move in this direction. If you look at the angle of this element, it's 45 degrees negative, right? So it's 45 degrees. So this thing does not want to get short, which means it's kind of like a support here that, right? It's kind of like a roller here. Sorry. A roller here that is at 45 degrees angle at this point. So it doesn't want to get short, and you can see that by looking at the deformations. Look, because this is a 45 degree. Now these two are identical, and they will always be identical because it never gets shorter. All of the movement happens on a theoretical line, right? That goes across like this, right? At a 45 degree angle. So I simulated a 45 degree roller by just adding some, a theoretical element into my model. Now, obviously, as long as this is 45 degrees, you can actually move this, right? And as long as it's 45 degrees, it will work exactly the same. Now, this also implies that if I want to, let's say, have a 30 degree roller, don't forget, right, this is, let's say, well, 63 degrees. So whatever's left from 63 is what I'm going to get here, right? Let me see if I can get it closer to 60. This one's closer. So it's kind of like 30 degrees in this direction. And you can make it happen by editing those nodes accordingly. And think of it like this. It has a local coordinate, right? Like this. So I have a, approximately 30 degree angle here. So my element is going to move on that line, right? On that line. So I can show the same thing here. Oh, that was not close. Oh, you know what? Let me show it here. It's a little better because it does not move. Okay. Oh, my pen lost its battery. So, but you understand what I mean, right, guys? So by changing the angle of this, I can move its local second local axis in the direction I want to turn that into a simulation of a roller. The only thing to keep in mind is to make sure that this has a very large area or a very large stiffness. You don't want it to have a very large stiffness because, see, the good thing about this is that I made it hinged on both sides, but even if I don't have that hinge, it'll still work. And you can look at the deformations at this. Those two have that 30 degree cosine between them, and it is moving in the direction I want. You can simulate it by making these hinged as well. That way you don't really need to worry about the moment resistance of this. But you can also reduce the second moment of area to simulate the same thing. So any questions, comments? Guys? You don't have to say anything, it's just asking. All right, let me switch to my next topic, which is on tapered sections. So that was another item that Dr. Chatbush asked me to cover, I think, over here somewhere. Yeah, over here. You'll see we have tapered sections or non-prismatic members. So you can have a non-prismatic member, meaning its cross-section is changing continuously. And believe me, its equations are very, very complex. So complex that for a mathematician, it might be fun. For an engineer, it's just not practical to deal with. So what do we do as engineers? So I already created something to simulate. So we have taper sections. One option is, okay, let's say I know the depth of this element at this location, and let's say it was 500 millimeters or 50 centimeters, right? And on the very far end of it, it goes down to 200 millimeters or 20 centimeters. So what do? One thing you can do is, well, you can add this and find it's the average of the two and come up with a 340 millimeters depth, and and then use, or you can use a smart. I know the average of 200 and 500 is not 340, it's 350. And I don't know if I have 350 here. I might not have. But you can come up with a smarter uh, average, because, as you know, second moment of inertia does not change linearly as the depth changes. It goes with the fourth power. So you can still come up with a smarter, average for this, rather than just adding the two and dividing it by two. But another option is to divide the section into two and use different sections in both. In this case, I used the largest section for that first half, and the smallest section for the second half. But here's the problem. Um, you have different loading conditions every time you deal with a different thing. So um, it's hard to predict what is a better approximation, other than dividing the element into even smaller and smaller and smaller and smaller sections. Here I divided it into, I think, 16 sections. Yes, I divided into 16 sections where the depth and the section properties are changing, um, as they should, right? As the depth is changing, the second moment of inertia is changing as the fourth power of it, the real value at those sections. And you can see the deformations can be very, very different. Look at this. It's over here, it's 6.47 millimeters. Then it went up to 7.96 millimeters. And then it went down to 3.17, and then 3.12, and then 2.94. I believe that is also what is observed in this case study here. So yeah, it goes up first and then slowly comes down. This is slope, but yeah, so depending on how you choose to divide and which sections to pick, you will have a different behavior. In this case, I think they never used the largest section. They're basically dividing it and then finding the middle point of each section, and then using the section properties in the middle of that section, which is probably a smarter way to do that. But if you use that awesome power of your computer by dividing into 16, and procedurally you can even divide it to 100, if you're really interested in finding the deformation or the load distribution across your um, tapered section, you can divide it as much as you can, and at some point it will be completely indistinguishable. And the load distribution is not going to be very different. Obviously, we covered that in the last time I was speaking to you, because this is a determinate structure. The section properties will not make a difference in how the load is distributed across. So it's all the same. Um, the same thing here in the shear moment. We don't have any axial loads, but I could add a little bit if you want, and you'll see that it will be the same for axial loads as well. So there will be no difference because it is determinate. But if it is indeterminate, well, good luck, figuring it out without using this. It would be really, really difficult, I assure you. So this is another, quote unquote trick to use the power of the computational approximation to simulate more complex behavior. You can just divide your elements. Keep in mind there are no hinges here, right? So it is just smaller sections, but there are no hinges. So it is basically simulating a tapered section. All right, any questions? Questions? I'm continuing. My last item that I want to cover is substructuring. Now, this is becoming less and less relevant, especially for structures like the ones that we deal with, guys, meaning, just frame elements, even if it's three-dimensional. A lot of times when you press that run/design button on your computer software like SAP, ETABS, or I don't know what else is out there. The most of the computational effort is actually going to the design part. Surprisingly, the analysis part, unless you're doing some sort of time history analysis or something really advanced, right, or pushover analysis where iterations take place, it's actually pretty quick. But in the past, especially, like I said, this is becoming less and less relevant. Engineers found smart ways to minimize the amount of work the computer will do. Especially back in the day, it was really difficult to invert really large matrices. They found ways to make those matrices sparse, meaning with a lot of zeros, which are easier to invert. And then they also did something called substructuring. Look at this beam here. This is a simply supported beam, supported in the middle, right? Because the loading condition is symmetric in this case, and we can actually simulate maybe even a distributed load would be the same. So I'll just remove those and add distributed loads instead. Oh man, this is not very pretty. Difficult to see. Let's see. Oh, now we got into the other structure. 1 second. I'll make this off. I'll make it cleaner. Just a moment. Yes. Okay. So take a look at this structure here, right? You have a simply supported structure and you have a distributed load on it and a point load in the middle of my simply supported beam. Because this is a symmetric beam, I can actually, if I don't want to invert a very large matrix, in this case, it's not going to make a big difference, but see, I have 3 degrees of freedom here, 3, 3, so this is going to be what? Yeah, so it's going to be 9 by 9, right? My matrix, my final structure matrix is going to be 9 by 9. If I can make it 6 by 6, by hand it would be easier. And if my numbers were much larger, maybe even for an older computer, it would be easier. So what we do is we say, okay, I know that at this point, this frame element is not going to rotate just from symmetry. Symmetry of the structure plus the symmetry of the loading conditions. It dictates that this point is not going to rotate. So I can say, I'll ignore this other half of the structure and replace this with a support that allows the structure to move up and down without rotating, right? When I do that, look at the moments, right? It's the same. I didn't solve the other side because I don't need to. I know it's symmetrical. So if I made this a pin, obviously it wouldn't work, right? Because a pin means it's a mechanism. It has to have some resistance. And the resistance in this case comes from the rotational restraint of this joint or node. So if I simulate that, if I know that these two will be the same, then I don't need to simulate the other side because it's perfectly symmetrical. So by using very smart boundary conditions, I can avoid modeling the rest of my structure. And it works on the distributed side as well. And you can see I changed the boundary conditions of this one. It's still symmetrical, so it still works. You can see 0.068, 0.068. Because I know this is not going to rotate, I can do this trick. Same thing with distributed loads, and you can look at the moment diagrams. They're identical. Even if there are negative moments, it's still the same, right? Shears are the same, so I know this shear. I know the other side is going to be a different sign, but I don't really need to solve it because I know it's just going to be a mirrored copy of the other side, and the same thing applies in these structures as well. So a little bit more of an advanced version of the same thing would be, take a look at this one. This is basically a uniformly loaded, 3-bay, 2-story frame structure, right? I have some moments, etc. And now let's take a look at how many nodes do we have. I mean, because of the boundary conditions, some of these are going to be just 0 rows, and we're going to know that there's not going to be any rotation, displacement, etc. So there are some blessings that come from the boundary conditions and makes it easier to solve. But we have far more degrees of freedom in this structure, right? And imagine this was a very, very large structure, right? If it was very, very large and our computer was not powerful, we might consider creating a condition where we say, okay, well, the structure is symmetrical, the loading conditions are symmetrical. Why don't I cut it right here in the middle and apply the same trick, right? Don't allow rotations, because why? Because I know that the rotations, well, who's rotating all this much? Oh, these guys. Let me just delete this for a second, just to be able to see the rotations here. See, the rotations in the middle are 0. So knowing that, I can basically, oh, I'm going to have to bring these back. Okay. Did I come? Yeah. Still some stuff to bring in. All right. This is fine. Yeah, that is fine. So knowing that the rotations in the middle are 0, I simulate the same thing by adding these elements, allowing it to rotate, move in the vertical direction, but not allowing it to rotate. And take a look at the deformations. Let's say 0.26 in the middle of the first span, same, right? 0.26. So 0.32 on the top floor, same. Even though I didn't model half of the structure, I only modeled one half, not the other. Of course, this only works if your loading conditions are symmetrical. There are other ways where you can simulate point symmetries, not just line symmetry like this or plane symmetry like this. I'm not going to get into those, but I just want to show you that there is something called substructuring that people use on a regular basis, or used to use them on a regular basis to simulate really large models. They still use them very often in SolidWorks, etc., when they're modeling, what I call, complex 3-dimensional objects, because their matrices get really, really large, and using those smart boundary conditions and symmetries actually save a lot of time, computational time, even to this day. So for our structures, not as relevant as it used to be, but substructuring is still being used for those cases. Take a look at this. So let's say I have a structure like this, right? I'll give you another example of substructuring. And this one's a little tricky. That's why I left it to the very end. But let's say I have a structure like this, right? Two columns and a long girder, or 2 girders on 2 different levels. And I have a very complex loading condition on them. Now, if you look at this, right, or if you look at the structure like this, just the structure, obviously there are a lot of degrees of freedom, and it may get really complicated. But as an engineer, we can look at it a little smarter and think that, okay, this is hinged on this end, this is hinged on this end. So this whole girder kind of works independently, even if it has some complex loading conditions on it, it works kind of independently than the rest of the structure. So I can basically take this and solve it separately as a simply supported structure with complex loading conditions, right? I find my moments, shears, etc. separately. Then you'll see the same thing applies over here as well, right? Because these they are basically simply supported structures, so we can solve them independently of the rest of the structure. You have to be cautious though. Let's take a look at deformations. So you'll see that the deformations don't agree perfectly. This is 22.56, this is 22.57. This would be especially problematic if the columns were softer or they were, deforming a little bit more. So in those cases, you'll have to know when this much shear, let's say in this case 1.1 kilonewton, is applied on the column, you have to figure out how much of a deformation is going to come here, and then how much of a deformation is going to come to this point, and then basically find out how much you need to add to the deformation of this element at each node. Obviously, on this first node, it's going to be exactly the same with this. If these two are deforming the same, so we'll basically add the deformation of these points to all of these points to find the displacements, right? The deformations of these intermediate points. So we kind of have to do this. So let me show you. I have to find, okay, how much here is coming? 1.1 kilonewton, right? I'm not going to get into the very details of it, but I'll put 1.1 E3, right? And I'll put it negative 90 right here. And it's the same for this one because these two don't affect each other. It just comes from here and pushes down. So I will put the same load here, and I can solve my column separately and look at the load on it. I mean, apart from some rounding errors, it's the same, right? So I can solve, if the structure allows it, you can do substructuring, solve the easier to solve parts of it separately, like this column being solved separately, right? As in this case. But I have to find the load path and understand the load path, right? So 1.1 kilonewton here. So this, after solving this, I understand that it's not going to affect my column. So I take the load that comes to the column and apply it to the column, and then solve it that way. Again, you probably will never do this because computers are so much more powerful these days. But it's a method that was popular and still popular in some parts of engineering to solve complex structures with less or fewer or less computational power.